Before I start today's session, today I'm planning to just give you give some introductory idea that how we formulate Hawking radiation in the context of curved space-time, because so far we have discussed particle production from the flat space-time. We have understood the significance of understanding Rindler space-time, that why it will be easier for us to just get a feel that how particle production can happen even from the flat space-time if I just change the observer's trajectory. And maybe today I will take the liberty of developing this Rindler particle production phenomena to introduce the topic of Hawking radiation. So I will try to go a little bit slow so that I also can understand that whether it is getting related to all of you or not. So at first, just let me start with the idea that why exactly it is a convention that you start with the Rindler and then move to the Hawking radiation. So let us explore today the near horizon geometry of the Schwarzschild space-time, mostly in 1+1 dimension, that means in 2 dimensions. Because again, that is only for the triviality I chose, or in literature you will see often that the 2-dimensional studies has been done first, and then they rigorously moved to 3+1. For 3+1 analysis, I would request all of you to please go through any standard books like Mukhanov, Birrell and Davis. Birrell and Davis do not have 3+1 thorough derivation. There is a nice book by Navarro, Salas and Fabry. That's a recent book, perhaps on the evaporation of the black hole, that is restricted to the Hawking radiation and stuff. So these books may help you to get the feel of this 3+1 dimensional analysis. So let us start from the Schwarzschild matrix. So of course, I know you are quite pro at Schwarzschild, and that's why I'm not going to that how Schwarzschild metric is the solution of Vacuum-Einstein equation. So that perhaps will be covered by TP or Patrick. So I'm writing this in natural coordinate, where I have taken G and C all to be 1. So capital M is the mass of the black hole, which is of course static and spherically symmetric. Within this R square, we have all this polar angle and azimuthal angle situated, and it can be written as d theta square plus sine square theta d phi square. So just for the to reduce the effort, I am writing it as a 2-sphere sitting everywhere in the TR plane. Now for the Schwarzschild metric analysis, let me have a distance from the, okay, so also the event horizon location, as we know that it is nothing but for the Schwarzschild event horizon is at this radius or at this radial distance. It is the event horizon of that particular black hole. And now let me take a small distance from the event horizon. So let me just represent that distance to be, let's say, x, which is less than twice m, but of course it is greater than 0. So this is how, let us take the event horizon near to the event horizon distance, which is just following this limit. With this, I can redefine, let's say, my radial coordinate small r in terms of x. So if I want to write that, then I am writing it r is equals to twice m plus x square 8m. This is how I am taking this redefinition. So twice m plus, because I am interested about the region which is outside of the event horizon, not inside. So r less than twice m is not at all my concern over here. So I'm happy to just check out for the outer most region of the Schwarzschild, and just you take a very small distance from the event horizon at r equals to twice m sorry, and you get in there. So this one is the short distance. This is how I am expanding r in terms of twice m plus x square by 8m. Now you may ask me that where is the linear order in the perturbation? You can take in principle that x, r plus x as your perturbation also. So if you do that transformation, you will see that this part will come up with the 1 over x character. So that 1 over x character as x going to 0 is basically not a very good candidate to see the geometry around the near the event horizon. So that's why it is convention to get the geometry properly around Schwarzschild. We prefer to take it as x square by 8m. Now if you just redefine this, you will get this. I have checked many times by my own calculation, so please feel free to see this whether I am writing it correctly or not. So here also you will get x square correction, but with respect to the twice m whole squared, this is the leading order contribution. I am ignoring that angular part is affected by this perturbation, so I am keeping this up to this. Now you can check out that only this part of the metric is basically flat spacetime metric. If you find the R2 or the Ricci scalar, you will get that this acts as a flat spacetime. So now to realize more or to see more in it, we can again perform some coordinate transformation. So let us take another coordinate transformation from this point. Okay. So let us have another coordinate transformation. Capital U varies as minus x e to the power minus, this is kappa, okay. I cannot write kappa in that mathcal mode, so please bear with me. V is x e to the power kappa t. With this new redefinition, actually today we will do lots of coordinate transformation to get into our priorities. So u equals to this and v equals to this. If I go by this, I know you can quickly tell me that this will imply your ds square in 2 dimension to be minus du dv. Just check this step by step, you will get the answer. Now on top of this, again I can take again a coordinate transformation. So these are just coordinate transformations, and if you are adventurous, you can actually go and plot them and see that how all these limits actually behave. So another transformation can be written, which is x is equals to kappa inverse e to the power some parameters I. So if I take this as my x, then again this metric in 2 dimension can be reduced to So I stop here now and just take you to the past, that when I was actually trying to build up the Rindler spacetime and its transformations. At that time, we all know that we obtained dA square in the Rindler look like e to the power 2a, the spatial coordinate in Rindler, minus d tau square plus d xi square. So this actually what we obtained for the Rindler spacetime using Rindler transformation on T and X. So now you can see that why people often say that black holes near horizon behavior in 2 dimension is something like Rindler spacetime, because you can just make a 1-to-1 mapping between these two, and even you can say that in Rindler we got the temperature of the thermal bath, what was produced in the eyes of a Rindler observer was in natural unit a by 2 pi. So I should get in the near horizon limit of black hole the temperature, if there is thermality, then the black hole temperature, it should varies as the kappa. I'm just making 1-to-1 similarity between these two spacetime metric, nothing much. So this kappa is basically tagged with a conventional name that is called surface gravity in black hole studies, and this is actually inversely proportional to the mass of the Schwarzschild black hole. So this kappa comes out to be 1/4m for Schwarzschild. For Reissner-Nordstrom it is separate. I'll come to that. So basically this is a clear-cut motivation. I mean, also this was a motivation for Hawking as well, that if my Rindler spacetime can disclose some sort of particle production from the Minkowski vacuum, then why not a black hole which can mimic under certain limit. Of course, I agree, under certain limit, if a black hole spacetime is reducing to a Rindler kind of spacetime, then why we cannot expect that black hole spacetime will also show us some sort of particle production. So this was basically the direct motivation of studying particle production in curved spacetime. Later, of course, Leonard Parker and Starobinsky, they all came up with the particle production in cosmological spacetime, where exactly we have a scale factor which is dependent on time. So simultaneously also Hawking developed that how to get the particle production from the spherically symmetric collapsing star. So this was also done. I mean, that is in a separate, with some separate notion or some separate terminology perhaps I have to introduce if I go by that how a gravitating spherically collapsing star shows the Hawking radiation. But at least for some eternal black hole today, what I planned for to tell you about the eternal black hole cases where a black hole spacetime is not changing with time, it is very much there. I don't know its collapse history. I only know that it's an eternal black hole, it's a static and spherically symmetric black hole lying there. So how we can perceive this thermality in the context of that. So after this, I will take you to the Reissner-Nordstrom spacetime. That was a concern from one of us, our colleague here, and that is a very valid concern what he raised day before yesterday, I think. Okay. So for the Reissner-Nordstrom, it is of course already known to you that it is a charged black hole, and you can derive the Reissner-Nordstrom solution same as the Schwarzschild if you take the Einstein equation and in the left hand side, and in the right hand side as a source you should use the energy momentum tensor for the electromagnetic field. So if you take an electromagnetic field and calculate its T mu nu, you will get and you plug in there in the right hand side as the source of the mass, you will get the Reissner-Nordstrom solutions, and there you will earn another correction in the so-called Schwarzschild metric, which we can write as this goes unharmed. Okay, so in here, people who are not aware or even aware, so let us just have a quick understanding what is extremal and non-extremal Reissner-Nordstrom black hole. So if I calculate from here the location of the event horizon, then we know that we require the condition that this goes to 0, and this is turned out to be the quadratic equation for R. So it will come up with the two solutions of R. That is quite understandable. And if I want to write what is R, this is twice m plus minus square root of m square minus q square. Sorry, this is only m. So here actually people draw two conditions. Number one, when we have m is greater than q, which actually give us the non-extremal Reissner-Nordstrom black hole, right? And another condition may emerge when you have m is equals to q. This is known to be extremal Reissner-Nordstrom black hole. So the ambiguity was from this extremal part. Now why? That is the catch. So if I incorporate the condition 2, that is extremal Reissner-Nordstrom conditions, then we can quickly see that if I take this 2 root to be r plus minus, and if I plug in m is equals to q, then it will of course give you r plus equals to r minus, let's say some r0. So it's a degenerate horizon where you are getting that the outer horizon and event horizon, they are inner horizon, both of them are same. Now why this is a problem for the particle production? The particle production problem is, I can just tell you very quickly without establishing the thermal bath temperature. If I see the temperature of the thermal bath in case of the Reissner-Nordstrom as well, this is quite standard, that it has to be proportional to the surface gravity of the black hole. And the surface gravity for the Reissner-Nordstrom is defined as so this is how the surface gravity for the Reissner-Nordstrom metric goes. And it is already evident to you that if I plug in r plus equals to r minus in here, then of course the surface gravity corresponding to extremal Reissner-Nordstrom black hole turns out to be 0. And therefore there is no thermality, at least for this degenerate horizon structure, that is for extremal Reissner-Nordstrom black hole. But of course for non-extremal Reissner-Nordstrom there is standard proof, and you can show indeed that the temperature of the thermal bath goes as the surface gravity, where r plus is not equals to r minus. But for the extremal black hole, of course, we are not able to define it. So I hope it is tentatively answering your question that why Reissner-Nordstrom cannot have Hawking radiation.
Yes and no. In the sense that for the extremal case, what we can say that if you do those kind of coordinate transformation you did for non-extremal case, it wouldn't give you the Rindler metric.
No, it will not give you Rindler metric. That I can show you. This is my next section, where I can show you that the extremal Reissner-Nordstrom black hole in the near horizon limit looks like an anti-de Sitter spacetime. So anti-de Sitter spacetime is a curved spacetime with a negative curvature, and it cannot look like Rindler in any limit. So that we can prove right now. Are you hitting towards that? But non-extremal can be reduced to, extremal cannot be.
Naively, one would think, even if it is an extremal, it is a black hole.
Yes, it's a black hole, but it has no surface gravity attached with it, because its horizon r plus r minus, it is degenerate by nature, and so that's why thermality will not emerge from them. And also if you do the near horizon approximation, whether to see that whether it can mimic Rindler or not, you will get that it is not at all like a flat space-time.
I was thinking to get a physical picture of why that is.
Yeah, so this is what I can offer you now. I cannot tell beyond this.
Anyway, this is what I was planning to present for the Saturday's presentation.
Okay, please go ahead and enlighten us, because I also need to know if there is something beyond GR we can get. Car black hole also has, but no, there also this kind of condition, I don't think so. Yes, for the angular momentum. Yes, for that also you can't. Car doesn't have the charge, but for the angular momentum, yes, of course. Yes, as of now, but I don't know. Maybe we will get something new tomorrow. But I think at least literature and physics say so as of now. So let us have, okay, let us not wipe out the Reissner-Nordstrom metric. Now, as there was a concern about the near horizon geometry of Reissner-Nordstrom, we can just have a quick look in it. So for the near horizon geometry, here I am taking the near horizon geometry from the outer horizon r plus to a small distance, let's say x. So again I will go to the x square redefinition. I will not keep it in here. So r equals to r plus x will straight away give you the form of the ds square. Please feel free to check it. Of course, it's approximation up to the first order of x. So minus x divided by r plus. So at first, please don't feel very uncorrelated. This twice and q, they all can be represented in terms of r plus r minus, because you have seen that they are basically related with each other. So r plus r minus, they have this relation. So we have two equation, two unknown. So you can represent r plus r minus in terms of mq and vice versa. So that's why you can write down the metric in terms of r plus and r minus instead of m and q. Feel free to do whatever you want. So I wrote down in terms of r plus r minus, and then when I took that near horizon approximation, the ds square turns out to be minus x by r plus 1 minus r plus dt square plus r plus dx square divided by x. Of course, the angular part is sitting at every point, so I am not repeating it. And then again, I can take another redefinition. As I said, that x to x square is a more nice looking transformation. R plus r minus 4r plus square and x square. So all these steps are given as an assignment. So if you want, you can just check out. So this basically this transformation again, if you impose, then you can see that what would be the fit of your ds square. So if I just take this final redefinition, it will give me ds square as I'm not doing the intermediate step on the board. You just need to find the differentials of x and move on. So please just check. And where kappa plus came as the surface gravity, So this is how it will look like in case of the near horizon geometry, but please don't be very happy about it. For the extremal black hole, now if I take the extremal black hole condition, extremal Reissner-Nordstrom, then of course my R plus is equals to R minus is equals to R0, and the near horizon limit which was applied on R plus, now you apply it on R0 as R0 because they are degenerate. So now you take your near horizon geometry is under this R0 is going to R0 plus X because it's an extremal black hole. So if I do that, I mean just from here to, if I just take my radial distance varies as R0 plus X, then starting from the Reissner-Nordstrom, you can quickly show that under this change, your extremal case will become so from this metric, if I focus only on the TR part of this metric and try to calculate the Ricci scalar in this dimension, that means R2, which actually gives us the curvature of the space-time, this R2 comes out as minus 2 by R0 square, which is less than 0. So a curvature, negative curvature space-time is known as anti-de Sitter space-time. For certain kind of energy, stress energy tensor, you can mathematically bring this solution that my space-time has negative curvature. It's basically look like a throat-like geometry, which was very popular in Randall-Sundrum geometry, and also it's called Klebanov-Strasler model in string theory. So all those are basically anti-de Sitter space-time. So anyway, so this is only ADS2 fellas, it is not ADS4. So in your entire space-time becomes, of course, ADS2. So this is not ADS4, this is only ADS2, and this is only happens for this kind of conditions, extremal black hole condition, where you can see that the near horizon geometry is basically a throat-like space-time, which is somehow wrapped, warped kind of a geometry. So this is how, this is I found very interesting to share with you. That's why I covered this up. Although I do not have any understanding from here to the non-thermality of the extremal black hole. For the thermality, I have only the explanations from the surface gravity, but this is a exotic feature which I thought to share with you for Reissner-Nordstrom near horizon. Please, you can make this calculation. This is interesting to just see that how it happens. Okay. So this is all I had to tell you about the near horizon stuff, and a clear motivation to see the black hole particle production. Now onwards this, please tolerate me. I will do several coordinate transformation to get to the standard understanding, and feel free to stop me if you are not, if you disagree, if you want any other explanation for anything. So again, my focus now will be Hawking radiation. So let me just quickly come to the point of coordinate transformation. I will be very much slow in just tell you something. I mean, this is how I learned. Again, I'm coming to the Schwarzschild. Please bear with me if I'm changing the metric signature. Please don't get confused. Sometimes I have used minus plus, I mean mostly plus, and sometimes I have used mostly minus. All the field equations are changed accordingly in my handout. So don't worry about that, they are consistent. It's just the negative effect of consulting many books while you are preparing notes. So now it becomes mostly minus 1. So of course I'll comfortably reduce this to only my R2, like 2-dimensional TR, only using the TR, but please don't forget at every point of TR you have a S2 sitting, it's in there. So this is actually what is now my something like GAB, DXA, DXB. Coordinate transformation, what the first coordinate transformation I'll use is known as the tortoise coordinate transformation. This is important, fellas. I can't leave these things without this mentioning this. I won't be able to develop the idea of the QFT, how it is built up. So yeah. So this is my first coordinate transformation that I have taken a r star, which is a function of r, and this is my r over of this r radial coordinate is changing to r star. So this is called tortoise coordinate, and if you change this, you can quickly write the differential of this. So dr star is varying basically as dr 1 minus rg by r. So this was written earlier, and then integrating both sides, you got that. You used suitably some integration constant and you landed up over there. So this is how basically the first coordinate transformation is taken, and under this you can quickly show that the Schwarzschild metric will become like 1 minus rg. Now the r became function of r star, and within the third bracket you have dt square dr star square. So this is how you can reparameterize the Schwarzschild metric, where this is the first coordinate transformation what we get. Then again reduce with the help of this r star, try to build up another coordinate system. So next coordinate transformation is basically small u tilde. These are basically u we always take as a null coordinates or light cone coordinates. So light cone coordinates in with the help of tortoise coordinate, it becomes t minus r star, not t minus r. I'm taking it as t minus r star. Please remember r star indeed is a function of r. So of course another v tilde can be formed. So this will become t plus r star. Sometimes I'm writing star as a superscript, sometimes subscript. So please again you bear with me. If I try to identify those lower and upper stuff, I'll be lost. Anyway, so r star and r star. Now under this transformation again you can write down dA square. So now your dA square Schwarzschild will become 1 minus Rg, R as a function of u tilde v tilde, du tilde dv tilde. This all I have checked by myself several times. You just, if you have not done once by your own hand, you may just see that how it comes. So fellas, please remember this structure. This is my Schwarzschild space-time in 2 dimension written on the board in terms of u tilde v tilde, where those are the null coordinates, all light cone coordinates, using the tortoise coordinate and the Schwarzschild time t and r star. This I need to develop the idea of ball body vacuum. So that's why I wanted to come over here. Cool. After that, let me have our favorite coordinate transformation in GR, that is called Kruskal-Jaeger coordinate transformation. Of course, Penrose transformation perhaps most favorite, but Kruskal-Jaeger is equally very much a potential candidate here. So Kruskal-Jaeger look like the Schwarzschild prefactored 1 minus Rg. Okay, please remember Rg is nothing but equals to twice m. So this is equals to Rg by R exponential 1 minus R by Rg. These all are very unique prescription of coordinate transformations. You can think that that people obtained this just in while they were dreaming or so, but no, they had their own compulsion to show that we have some coordinate transformation in GR which can give us a very regular behavior across the horizon. That was the first priority for them. So then they tried to explore all sort of coordinate transformations in general relativity, and they hit that event horizon. Singularity at event horizon is very much the characteristics of Schwarzschild coordinate only, t and r. You can indeed remove that, but of course you cannot ever be able to remove the physical singularity at r equals to 0. What Vishnu was saying, that the Kretschmann scalar always diverges at r going to 0 limit. So that's a test for the for whether you have a true singularity in your theory or not. Yeah, so exponential 1 minus r by Rg, of course exponential, so we left something u tilde v tilde, so just bring them over here. You want to change from that as well. So so this is how Kruskal-Jaeger coordinate transformation will look like. I mean, you performed the coordinate transformation and then GTT component of Schwarzschild look like this. So this is how, if you do, you can write down d square is Rg by r exponential 1 minus r by Rg. So just see the beauty of bringing in this exponential over here, because anything on top of exponential, if it is becoming 0, we become relaxed. It is of course 1. So we are safe at least at the horizon. R equals to Rg is no more a undue divergence in case of the Schwarzschild coordinate, the way we get it in the dr square, in the denominator of the dr square. I mean, let us just understanding why we are doing it. I hope the rest will be easily done. So this is how we got a new metric in terms of r, u tilde, v tilde and all such. It can be written in a more nicer form, which we called the light cone coordinate or null coordinate in Kruskal-Jaeger coordinates. So Kruskal-Jaeger, if I take it to its u and v version, then I would love to see that if it has its own light cone version. So yes, it has indeed. So small u is the light cone coordinate in Kruskal-Zecker coordinate transformation, and this look like, again exponential is my TRP, so I will retain that feature, and I will show you how Kruskal-Zecker coordinate is very much a regular coordinate across the horizon. Do we have question or comments? No, please feel free to share with me if you have any. Oh, okay. So after this, I know you will be happy to see the form of ds square in Kruskal-Zecker coordinate system. It becomes like this. So this is where you can tell me that if my R is going to RG, the fit of the metric is quite nice. It is near horizon. This metric look like a du dv, right? So which, I mean, another space-time we have in our mind that which look like du dv in its null coordinate, that is Minkowski space-time. If you take Minkowski flat and transform t plus r equals to u and t minus r equals to u and t plus r as v, you get ds square as du dv. So basically Kruskal-Zecker coordinate near horizon, you can show that it is nothing but like a Minkowski coordinate. So across the horizon it is quite a regular feature it can display, which of course tortoise coordinate do not have. If you remember the transformation of the tortoise coordinate, it is coming up with a log sitting in there, and within the logarithm argument you have this dangerous factor sitting. So for r going to rg, tortoise coordinate exhibits divergence. It is not regular near the horizon, I mean at horizon. So it can give you good answer only for those radial distances which is greater than rg. So if r is greater than rg, please play around with tortoise coordinate, nobody will mind. But if you are studying something across the horizon, then you are lost if you are going by this, because this transformation itself do not have any r going to rg limit, it's minus infinity. But it is good for asymptotic observer though, right? So cool. After this understanding, this actually I will exploit to build up the vacuum state in the curve space-time. Okay. So there are many algebra can be done on this. Now straight away let me come to the field quantization. What we discussed in the context of Rindler, we will do something around it today. So I will not be able to derive step by step the Bogoliubov transformations and all, and I don't want to go into this because nowadays you can get it from any lecture notes or any book, but I just want to give you the idea which I found very profound in the semi-classical gravity, that how we define vacuum state for the observer perspectives. But yeah, I hope the motivation of work will be clearer to you. If not, I am open to discuss at any time. Okay, so field. Of course, please write down Klein-Gordon equation in your mind in a curved space-time. Write down an action. Of course, in 2 dimension I'm talking about. So I can write down the Klein-Gordon action in 2 dimension as, let's say, for a massless scalar. The book by Fabry and Navarro-Salas, they have done this entire calculation for massive as well as for 3+1 dimension Hawking radiation. So you can look into that book. I can send it, share it with you if you want. I have that. Of course, I have to take a root over minus g, which I missed writing earlier. So of course, I will absolutely exploit your already built up knowledge of writing the solution of Klein-Gordon equation in terms of the mode solutions. So from here, I can write down, let's say I want to focus as of now on the tortoise coordinate one. Okay, so the light cone coordinate using the tortoise coordinate was nothing but u tilde was t minus r star and v tilde is t plus r star. So if I want to write in terms of u tilde and v tilde, so let's say I have field solutions such as phi some a tilde u tilde plus, let's say, some b tilde function of v tilde. So this is of course using the tortoise null coordinates. Now the same thing I can write down with the help of Kruskal-Jaeger null coordinates u and v, right? So of course you can write down the field solution in terms of this so this is how I can tentatively write their solution. Of course, I have not said anything about the quantization or the expansion in terms of the creation and annihilation operator that I am going to do. I hope you will agree with me. So in case of tortoise coordinate, when I write down this in terms of t and r star, this particular metric can be reduced. I mean, if I take for an asymptotic observer condition, please try to understand. If I would not be able to cover the whole stuff, at least let me motivate to the Bolware vacuum. Next day I can pick up from Hartley-Hawking vacuum. So let me just tell you about the limit of this metric. I mean, you can tell me if I take r tends to infinity, this was Kruskal-Jaeger. So here, sorry, this was the tortoise coordinate u tilde v tilde. If I take for the tortoise coordinate metric r going to infinity, remote observer or asymptotic observer limit, will you agree with me if I write down that dA squared will become under the tortoise coordinate true? And then further, you know that this I can write down again, but just by using t minus r star and t plus r star as so this is basically like a Minkowski for a remote observer. So for r going to infinity, it is also absolutely evident from the original Schwarzschild, and as well it is evident from here. So under the, so I was trying to focus when I was trying to motivate this vacuum state and all, that T, time translational invariance of the metric, has to be seen very carefully so that I can formulate or I can construct a positive energy solution. That is what I said from the day 2. So here also just focus on T. This T, the Schwarzschild time, is able to give me a positive energy solution for under this limit in the tortoise coordinate. So associating with T, I can think of the positive energy solution for the particle, of course for an observer who is sitting asymptotically distance apart from the black hole. So this positive energy solution under this T, whatever the vacuum state you can construct, is known as the Bolware vacuum. Is it all right? Because now you are eligible to construct a vacuum state under this condition. And then you are saying that, okay, I can now design a e to the power I omega t kind of a wave function or mode solution for a field, which will give me positive energy solution if I hit it with a creation operator. I mean, it will create a particle which carry positive energy. So I am able to write my field theory under this limit for an asymptotic observer. So for this observer, Bolware vacuum is a very much defined vacuum state. And as it is a vacuum in his eyes, he doesn't see any particle in that. It's an empty state for him. Is it all right up to this? So please remember that Schwarzschild time t is not a very, Schwarzschild coordinates is not a very good coordinate near horizon. For r equals to rg, t and r is not a very good candidate. That's why we performed all these coordinate transformations. So I am not able to write down a good vacuum state with respect to T and R near a Schwarzschild. We saw that it has its ambiguity. It shows some coordinate singularity there. And now if you are writing the mode solution in the Bolware vacuum for a certain field, how will you take it? You will take it e to the power, let's say some frequency t minus r star, something like this. I mean, I'm just writing it in a hand waving way just to give you that feel. Now I hope you will agree with me. Already I told you the tortoise coordinates r star is absolutely wrong choice for r equals to rg due to the log term. Within the log you have the argument r by rg minus 1. So if your r star is near horizon, then this is actually telling you that this kind of mode near horizon will be fluctuating extremely. It's in infinity. Just replace r star with a log r by rg minus 1. Use your r going to rg limit. You are there. So your well-behaved mode at infinity near horizon became huge fluctuating one. And with respect to this mode, if you are able to calculate the so-called energy momentum tensor or energy density in the at the horizon, it's infinity. It diverges. With respect to this field modes, if you decompose T mu nu, these are 2-point correlation functions, phi phi prime. They will all diverge near the horizon. So this is absolutely like anarchy with this coordinate system. If you want to forcefully go to the near horizon and try to explore your all such QFT stuff, you will get absolutely lost. You will see that, oh, I am seeing enormous fluctuation of the field over there. I am seeing absolutely the energy density which is diverging. And if I have this diverging energy density, I am seeing this, let's say, then what I will conclude? That enormous energy density should have a back reaction. it will actually completely jeopardize the classical solutions on which you are working. So try and understand, fellas. In the morning, Patrick told that T mu nu is the person who is making the space-time curved, or with the influence of which we can see that, okay, in one hand I have energy density, and other hand we have curvature. Here also, if you have a diverging T mu nu, that means a great value of expectation value of T mu nu, that means it's a very significant source. That source has capability, it will completely jeopardize your leading order Schwarzschild solution. It's infinite. But if it is finite and not a diverging, then we are safe. That okay, we are doing some perturbation theory, we are not doing some non-perturbative field theory over here. At first I motivated the fluctuation writing the field mode. Then I just a little bit stretched my analogy with the stress energy tensor vacuum expectation value. Trust me, fellas, if you just read between the line of any book of this semi-classical theory, you will get to generate this idea that why every time I'm talking about that vacuum energy relating to that curvature, relating to that divergence or such. Did you raise your hand, Deepa? Please ask, even if you're not sure. Locally it conserved T mu nu. I completely understand. And one more thing, I know where maybe you're getting in. This is a renormalized calculation what I'm talking about. I have subtracted the 0 point edge, the renormalized value will be diverged. But if I do it with respect to the Kruskal-Zecker and I remove that 0 point energy contribution, that becomes finite. Were you going there? Yes. Yes, you're right. This is a renormalized value get diverged. That is the problem with the Schwarzschild coordinate. This is a beautiful calculation, Birrell and Davis chapter 7 or 6 perhaps. So fellas, this is we therefore cannot define vacuum state for an observer in the near horizon geometry, in the near horizon region described by T and R star. You are eligible to do it only for a remote observer. And that's why Bolware vacuum is, let's say, the potential candidate for an asymptotic observer. Now, who is the very universal vacuum concept? That corresponds to Kruskal-Zecker. Because Kruskal-Zecker is itself regular across the horizon. See, at R equals to Rg, you have a well-defined metric. So across the horizon, Kruskal-Zecker is very much prominent. And we can have more decompositions in terms of Kruskal-Zecker by defining something called Hartley-Hawking vacuum state. And then my asymptotic observer, Bolware vacuum is 0 for him. So I will bring the analogy of this Hartley-Hawking and Bolware vacuum as my Rindler and Minkowski, so that you can at least understand that why I have taken this path to show you the particle production. So I don't want to take Apratim's slot, he'll be angry on me. So if you have any question, we can take for at least couple of minutes and then we can start from this next day. Tomorrow also I have my slot. Any question? So I know this is a bit of abstract, but don't feel like that. It is only I did some coordinate transformations. I only tried to tell you that whether the field modes are well behaved or not. I only tried to tell you that whether across the horizon I am eligible to define my field theory or not. This is nothing very much exotic I'm doing here, and I did everything only in 1+1 dimension. So I picked a very comfortable example. You can do it in 3+1. That is very rigorous, but cool, that can be also done. True. For freely falling observer, if you agree with me that he will see this T mu nu diverging basically. So for him, basically a freely falling observer, the Bolware vacuum is absolutely a messed up condition. It's an unphysical condition. People often tag it as an unphysical. So for a freely falling observer, if I am taking quantum fluctuations into account, then he will see that plethora of energy, I mean a huge divergence in energy density suddenly happened around the horizon. So yes, for him it is also a very uncomfortable situation where he will see this kind of infinity appearing in the Bolwer vacuum. For the Kruskal-Zecker, it's tricky. He will perceive thermality, but very nominal, not much. They have their concrete proof along that line, but I will always take Hawking radiation as perceived by some remote observer, because that is how we can fashion our detectors. Of course, I don't know about the space-based, whether they have any agenda to show particle production or not, but space-based means it's like a mode of like a static observer in black hole space-time. I'm not saying LISA will revolve around a black hole. I'm saying if we can design something, then that detector has to be constant in such orbit and orbiting the black hole. That means it has to maintain some acceleration. So that detector will also see particle production in Kruskal vacuum and under vacuum. These things can be done. These are very easily can be done actually from the field correlation functions. I can quickly show their thermal correlations. They are following from the thermal field theory correlation functions.
This is the actual particle production, not thermally.
No, this is, oh, I got your confusion. Actual particle production means this is for the eternal black hole. And there is a difference between the physical picture of a collapsing body, Hawking radiation, and Hawking radiation from eternal black hole. So eternal black hole one is, that means black hole is already in a thermal bath. It is trying to make itself in equilibrium all the time. It is in thermal equilibrium. So for the eternal black hole, the picture is like my black hole is immersed in sort of thermal bath, and my black hole is radiating the particle. Black hole is trying to be always in that equilibrium. So that is the TH. This is the picture of the eternal black hole one. But both depicts ultimately the particle production as a real one. You cannot say this is fictitious or so. The analogy is same. Virtual particle from a vacuum state, one particle will go inside, another particle will remain outside. Now the particle which is going inside, it is carrying negative energy. Now this negative energy comes inside the horizon. Outside the horizon, I cannot fashion any negative energy particle. Even if you say that my virtual particle is negative energy and it is coming out of the horizon, it has to annihilate quickly. Because the virtual particle, I mean, when people say that this particle production is happening near the, I mean, when you have taken, let's say, a quantum field near to the event horizon of a black hole, so vacuum fluctuation is always there. So basically it's a particle antiparticle production.
No, antiparticles don't mean that they have negative energy.
Absolutely. Outside the, true, I completely agree. Outside the horizon, antiparticle is absolutely with a positive energy. But when you are entering the horizon, T gets space-like. All your T are flipped, TR coordinate flipped. So the killing vector structure inside the event horizon is something different than the outside. So you can fashion a negative energy particle, and that's why you actually interpret that how black hole loses its mass.
Actually, I got confused because the other day you were saying what happens is that for particles produced near the horizon, one particle gets inside the horizon, one outside. But it is produced outside the horizon. So outside the horizon, it is produced with a positive energy.
Yes, yes.
Now you're saying that is what is going inside, and once it goes inside, that is what.
You can think it of like a negative energy particle. The outside one has to be positive, because if it is negative,
Created outside with a positive energy.
yes, that is an antiparticle with positive energy. You are quite right. It's a plus. Yeah. Same particle. You can, yes, you can see the flipping, because your entire killing structure is now changed. Na? T and R, they have flipped among each other. Time-like became space-like, space-like became time-like inside the horizon. So there is a very nice paper by Amos, Ori and all. They are trying to explore the particle trajectory and all inside the black hole. So they are doing some stuff and trying to match the solution in the event, near to the event horizon. These are very recent paper and PRLs.
Then you explain the flip of the energy.
Yeah, that can be done. I don't remember exactly that how to calculate the zeroth component and show that it comes out as a negative, but it can be shown, Deepa. I will search the literature and can suggest you. So that is how black hole loses its mass. And the negative, you cannot design negative particle roaming freely, negative energy particle. Even if you are designing, you have to justify that within delta E, delta T, it has to be annihilate. I mean delta E, delta T, H bar, satisfying this, you have to annihilate that, even if you are considering negative energy states. So nothing we can make unrealistic. So that is why the positive one will come out. And of course it's a pop. When that positive energy is moving towards the asymptotic observer, we often say that is drag energy from the gravitational field itself. It actually takes the energy from the curvature itself and move out. So this is how we say that black hole loses its mass. So we can pick up from here tomorrow if you do not have any other question, but please don't get lost. I didn't do anything very exotic what we didn't know earlier. You do not have any explicit interaction, that's what you mean.
Yeah. So when I write the mu, I write it for the matter field. I don't put any energy from the gravitational field. So how is
Do you have root over minus g in your theory?
yeah, perhaps we do.
Yes, now you take g and expand it in terms of, let's say, g mu nu plus h mu nu. And that h will actually interact with all the matter fields sitting in your theory. This is the catch, the minimal coupling or non-minimal. Even in the minimal coupling setup, root over minus g interaction is always there. You have, let's say, a pure gravity sector in your theory. Suppose you have a pure Einstein sector here, and you have, let's say, a simple standard model Lagrangian. If you take root over g to be, I mean, you perturb your metric g mu nu going to g mu nu plus h mu nu or eta mu nu plus h mu nu, this will be infected. Sorry. This will be h. A 1 plus h you will earn to the power half, and that h actually coupled with LSM. They are suppressed by 1 over MPL Planck, I understand. You will be not able to see the signature of that model directly, but 1 over MPL will be there, the gravitational coupling strength I am talking about. So it's very much sitting in your theory all the time. Now if you want to put something from your own hand, then you incorporate xi r something else standard model. Those are explicit coupling you are putting in. So that's why I said that it may extract energy from the gravitational fluctuation as well.
Yeah, it's not just the quantum.
No. So the dark matter people, they often do this, that minimally coupled dark matter with the gravity or non-minimal.